I am going to hop into things, and if people are trickling in, it's okay because the first bit is just introduction. So welcome to my ACCU 2021 talk. This is my first ACCU conference if you don't count the ACCU Autumn that I went to back in 2019. I'm going to be presenting my talk on C++ concepts versus Rust traits versus Haskell typeclasses versus Swift protocols, which this was the initial title slide that I had. And as a bonus, I'm actually going to be including the D language, which has a language facility similar to these, which is called type constraints. But my title was already long enough, and the initial time that I submitted this, I didn't include D. So the working title is Concepts versus Typeclasses versus Traits versus Protocols. My name is Conor Hoekstra. This is the About Me slide, or this is not the About Me slide. All of these slides can be found on the my GitHub page under the talks repository. So there's going to be a 2021-03 ACCU folder that has both these slides to this talk and the lightning talk that I will be giving at 1 p.m. Eastern Standard Time later today. So this is the About Me slide, the visual graphic About Me slide. So I work for NVIDIA on the Rapids team. Rapids is a suite of open source libraries that is focused on GPU accelerating data science. So if you're familiar with libraries, Python libraries like pandas, we are basically building up GPU analogs of these libraries that can be run on the GPU end to end. So if you are working with data science libraries and you're looking to accelerate your work, definitely check us out at rapids.ai. I have a podcast that I co-host with Bryce Lelbach called ADSP the Podcast, which is an acronym for Algorithms Plus Data Structures Equals Programs. I will provide a link for that in a sec. I also have a YouTube channel. I also run a Programming Languages Virtual Meetup that runs every Mondays at 8 p.m. Eastern Standard Time. We last year in 2020 worked through the structure and interpretation of computer programs, and we wrapped that up in January of this year. And now we've moved on and are working our way through category theory for programmers by Bartosz Maluski. Oh yeah, I can try not to move the camera as much because I'm not using my clicker due to my limited number of USB ports on my workstation. And last but not least, or second from last but not least, I am a C++ developer. So on my day-to-day job, we code in C++ 14. We'll be upgrading to C++ 17. But I also am a programming language enthusiast. I'm learning, multiple languages at any given time. Haskell and Clojure are two of my top 5 languages next to C++. And my favorite language by far is APL. I'm not going to say anything more about APL, but expect to see more talks from me in the future talking about APL. This is a 3-symbol expression for detecting whether a string or an array of numbers is a palindrome. So APL is known for being unreadable, but that's just because folks don't know how to read it. But anyways, like I said, that's all I'll say about APL. So all of the links that are corresponding to sort of the information about me can be found here: podcast, YouTube channel, rapids.ai, and the Programming Languages Virtual Meetup. It says Toronto, but it is a virtual meetup now and forever. So let's hop into this talk. The first thing I want to say is that this is not a language war talk. This is going to be a language comparisons talk, which is different than a language war talk. So if you've seen any of my tweets or lightning talks in the past, you will know that I love all programming languages. This is a tweet from back in October of 2019 that I highlighted in a lightning talk at Meeting C++ 2019, where I basically am encouraging everyone to be kinder to our programming developers in other ecosystems in other languages. I see on Reddit a lot, which is not the best place to go and look for sort of camaraderie, but I see a lot of bashing of different programming languages. And I think that every programming language, whatever your view of it, there is something to be learned from that programming language. Another tweet that I tweeted out once was a quote from Guy Steele, who's one of my heroes and the people that I look up to. He was giving an AMA at the PLDI, which is the Programming Languages Design and Implementation Conference back in 2020. And he said, "I love all programming languages," when I was asking him about APL And yeah, it's so awesome to see someone that I look up to so much saying this. And I really encourage everyone to try and take this more point of view. And so the point is, this is not a language war talk, even though we're going to be comparing languages. This is a language comparison talk. And the second thing I want to highlight is that this is a part one of a two-part talk. So I started preparing for this talk thinking that I was going to give a really, really technical comparison of all the different compile time, runtime features of these language facilities. But this is a super, super, super deep topic. And this is the beginner introduction to the topic. It is not going to be looking at the technical differences, which of these language facilities support associated types, stuff like that. Look forward to that in part two. This is basically an introduction to how do you build simple versions of a Rust trait or a C++20 concept, and what are the different categories that these sort of language facilities fit into. Set your expectations that this is sort of the beginner talk, and if you enjoy this talk and are looking for a more technical, in-depth version of this, expect a part two at some point in the future. So this is going to be the agenda for this talk. There's going to be 5 sections. I will pause at the end of each section to try and answer any questions. Depending on how many there are, I might only answer 2 to 3 to 4. But my goal is to leave 5 to 10 minutes at the end so we can address any outstanding questions. And I'll be in the hallway track afterwards if folks want to grab a table and talk about any of the stuff that's covered in this talk. So the first section is going to be an introduction. It'll be about 15, 20 minutes. We're going to try and burn through it pretty quickly of how I came to give this talk. Then there's going to be a short section highlighting generics and parametric polymorphism and sort of defining a couple different terms. Then we're going to look at 2 different examples. One is a super simple one, and then the second one is a little bit more involved, but still pretty simple. And then the final section will be my final thoughts on these 5 programming languages. So hopping into the introduction. This story starts in 2018 when at my workplace, we had a functional programming study group where we decided to work through a course that was an introduction to functional programming. And this course was given by a very well-known individual in the programming language community, Eric Meyer. If you saw one of the lightning talks yesterday where it was C# 9.0 or 5.0 records being introduced, Eric Myers has been very involved in the development of features that have been added to C# in the past. And we worked through the first few chapters of the textbook that came with this course, but then decided that it was a little bit out of date and that we wanted a more modern textbook. So we switched to Real World Haskell. And if any of you have read Real World Haskell, you'll know that chapter 6 covers type classes. And at the time, I knew about C++ concepts that were slotted to show up in C++20. And this was the first dotted line connection that I had between these 2 programming language features or facilities. It seemed very similar that what sort of type classes we're providing for Haskell was similar to what concepts we're going to be providing for C++. So this was the first dotted line between C++ concepts and Haskell type traits. Then roughly a year later, I watched a talk by Dave Abrahams, who I'm sure many of you are familiar with, on protocol-oriented programming in Swift. And we are going to look at a clip from this talk. As you can see, Dave gave himself the title Professor of Blowing Your Mind. It's an awesome talk. I believe it's actually ranked number 2 of all-time WWDC talks. I could be wrong about that. It might have been one of Dave's other talks, but it's a fantastic talk. And let's take a look at a clip from this talk.
Of course, I'm talking about protocols.
All right, this is not playing, so we're going to try this again.
Of course, I'm talking about protocols. Protocols have all these advantages. And that's why when we made Swift, we made the first protocol-oriented programming language.
So question for the chat, was there moving video? There was not on my side, so I assume it did not stream to your side. We will continue on, but maybe I'll hop out and hop in again to see if we can get it moving. But yes, you heard what Dave said, the first protocol-oriented programming language. And this brings us then to the next point in this list. So first was Haskell in 2018. Then just over a year later in 2019, I watched this talk in December. And then just a month later in 2020, in January, I was listening to a podcast called Magic Read Along, which is the inspiration for Bryce and our podcast, ADSP. And the two hosts say the following.
I just watched a video today on Swift and its and like their protocol-driven development or protocol-oriented development. And yeah, or no, it's POP. I guess okay. It was protocol-oriented programming. And they just basically introduced type classes, and they were like, "We invented this. This is amazing."
Is it actual type classes, or is it just like interfaces?
It's interfaces that you can extend ad hoc on the fly. Like and basically you can have as many constraints as you want. It's basically type classes. So I posted the 1988 Wadler paper.
So we're going to revisit this in a little bit, but basically, as you just heard, they're linking type classes now to Swift protocols. So at this point, I now have this sort of mental model of C++, 20 concepts, Haskell type classes, and then Swift protocols. So you can see once again that they're linking type classes and protocols from Swift. And the paper that they mentioned was 1988's How to Make Ad Hoc Polymorphism Less Ad Hoc by Philip Wadler. We're going to revisit this in a little bit, so I just thought I'd highlight it now. But this is basically the paper that introduced type classes. And this brings us to our fourth and final point in this journey, is that literally 4 days later after I listened to this podcast in 2020, I was on Reddit and I saw a post that was linking C++ and Swift that talked about a core question. And this is that question. So the influence of C++ on Swift, which links to the core question, which is going to bring us to our first digression of the talk. So the question is, what are the similarities and differences between C++ and Swift? Any guesses to who asked or who answered this question? Who has the top answer on this question? It is a person in the C++ community. I'll wait 5 to 10 seconds to see if anybody knows. All right, I don't have any responses. Herb Sutter is incorrect. Strustrup, incorrect. The individual, you're close actually. No, not Phil, but not Phil Nash. Strustrup is on the design committee, and this individual is also on the design committee for C++. And that individual is David Vandervood, who, as his byline states, is on the C++ committee and the direction group member. Or sorry, I meant to say direction group, not committee. But he is both a committee member, ISO C++ committee member, and one of the 5 individuals in the C++ direction group. So he's also the author of the very well-known C++ templates textbook. And we're going to take a look at David's answer. We're not going to read the whole thing because it's very lengthy, but it's worth highlighting some points. So the first thing he says is, remember that the original designer of Swift was Chris Lattner, who started and led the LLVM project. LLVM is written in C++, and the Clang C++ compiler is one of the primary drivers for its continued development. He then later on says, when it came time to select a lead Swift compiler engineer and a lead Swift standard library designer, who did Apple turn to? Doug Greger for the compiler and Dave Abrahams for the library. Both were some of the main contributors to the C++ 11 standard and widely recognized as world-class C++ experts. So here, David basically pointing out that 2 of the main compiler and library engineers on Swift came directly from C++, which I think is just super fascinating. And last but not least, David mentions at the end, all this to say that Swift, oh man, I just spilled some tea, which is not great, but we're gonna move on because it's not too bad. I apologize for that. All that to say that Swift was tremendously influenced by C++. Apple does not acknowledge this. I've been told that it is because more senior Apple decision makers dislike C++ at a personal level, in part because of the bitter rivalry between C++ and Objective-C in the 1980s. So David's pointing out that Swift doesn't like to acknowledge that they're influenced by C++, but actually all of the people that work on developing C++ in all of the talks widely refer to when they borrow from different languages. So it's more management that doesn't like acknowledging it. But the engineers, especially Chris Lattner, if you've listened to any of the podcasts that he's been on, he is very quick to mention the influences that other languages had on Swift. So to recap, These three individuals worked on Swift, and that's Chris Latner on the left, Doug Greger in the middle, and Dave Abrahams. And all three of them have some relationship to C++, so much so that the photo of Dave Abrahams on the right is actually a photo of him right next to John Kolb. For those of you that don't know, is the organizer of the CPPCon, C++ Now conferences, and the creator of CPP Chat. And yeah, someone in the chat saying Doug Greger is the author of Variadic Templates, which is a very, very useful feature that is utilized heavily in C++. So this brings us to an inner digression, which I said we'd sort of come back to when I was referring to the Dr. Boolean Magic Read-Along podcast. And I saw this tweet at one point. This was, I believe, April of 2020, which was the host, John Sundell of Swift by Sundell, as a podcast saying that Dave Abrahams was going to come on and asking for any questions. And sure enough, I tweeted and said, can you get a comment from the episode that mentioned that type classes was just copied from Haskell from Brian Lonsdorf, aka Dr. Boolean. And this didn't get brought up on the episode, but Dave Abrahams responded on Twitter saying that we never claimed to have invented protocols for Swift. After all, even Swift's predecessor, Objective-C, has a similar feature called protocols. We were open about stealing great ideas from programming languages, including Haskell. But Swift's protocols are not type classes. They were designed to be great for generic programming, for which associated types turn out to be important. And these papers are linked in the same GitHub repository where you can find these slides. But interesting to see that Dave is basically pointing out that there are some material differences between Haskell type classes and Swift protocols. And we're going to go into the most digressions within digressions that I've ever done in a talk, because this is a longer talk that I'm able to. And after the first time I gave this talk came out online, both Dr. Boolean from Magic Read Along and Dave Abrahams watched the talk. Dr. Boolean responded, just to point out that I did acknowledge that we were totally wrong in what we said earlier. So that's awesome just to see people being friendly. I pointed out that there was a longer version of this talk, which was not the talk that I previously gave, that has sort of the explanation of this dialogue back and forth. And then Dave Abrahams followed up once again on this Twitter thread saying that the talk communicates the language flavors really well, and that you can see that something we're going to get to later, the constrained versus consent approaches, is highlighted at slide 14, which we are going to see in a bit at the 14-minute mark, which we haven't gotten to at this point. But the more important part that he says later is, that said, I think that Rust traits circa 2012 provide all of these features except possibly the last, composed copyable values and more accessible idiomatic in Swift. Traits arrived in 2012, so I was wrong to claim the first without at least a mainstream, and even that's arguable. So saying basically that Swift being the first protocol-oriented language, you could argue that Rust could have made the same statement. And with this, we are going to pop off our three digressions. So digression number 1, digression number 2, and digression number 3, which brings us back to the initial post on Reddit, which is the influence of C++ on Swift. So very quickly, the things I want to highlight from here, because at this point, you're sort of getting the idea. Swift protocols and Rust traits are very similar. And Mr. Mobster goes on to say that this is why I'm saying that Swift protocols are more similar to Rust traits. And that, of course, we have C++ concepts which are very interesting as well. They are somewhat like traits and protocols. So this is sort of the full circle. Now I have C++ concepts, Haskell type traits, Swift protocols, and Rust traits that are all sort of being dotted line linked to each other as very similar features. So this is the sort of end of the story of how we got to giving this talk. And then I started doing research into this talk and found a ton of other videos that are highlighting this relationship. So we're quickly going to go through those. The first is a video from Context Free, which is one of my favorite YouTubers online.
TypeScript structural interfaces, nor on Go interfaces, nor on Rust traits, nor on Swift protocols, nor on Haskell type classes, nor on standard ML modules. Instead, I'm going to talk about C++ 20 concepts.
So the video is still not playing, but I think it's okay because none of these are super meaningful to the talk. But yes, the next video is going to be from the LLVM 2017 talk by Slava Pestov and John McCall.
So Swift has a very powerful generic system, a very powerful system of constrained generics, and those are expressed by what we call protocols. Protocols are a lot like features that you see in other languages with first-class generic features, such as signatures in standard ML or type classes in Haskell.
The next time I saw this came up was during the C++ London meetup, where they did this joint series between the C++ meetup and the Rust meetup, where two individuals pointed out this relationship. The first was Pias.
Traits are closer to concepts, but they are not exactly similar to, they are close to concepts, but there are still differences.
And the second is Hendrik, who I believe also spoke at this conference.
And traits are similar to what we know as interfaces in languages like Java or C#. These generic functions work similar to templates in C++. And if you are experienced with the newest C++ standard, so C++ 20, you might think of this. So I have a generic function which I constrain to fulfill a certain interface. This can be seen as something similar to concepts and constraints in C++.
Next up is from the same series, James Munns, who refers to a talk by Marin, which we're going to take a look at after.
There's a really wonderful talk by Marin at Rust Fest in 2016 where he goes over the Rust that could have been.
Let's take a look at a highlight from that talk.
And then at some point, we got more Haskell people on the team, and we all started agitating for a type class kind of implementation interface thing that we ended up now.
And this brings us to a digression of one of my favorite quotes from one of my favorite podcasts, which is the following by, I believe his name is Jared Roche, who said, "I've been referring to Rust as a love child between Haskell and C++. So I'm not a Rust expert by any means, but I sort of think of Rust as C++ plus Haskell, or maybe C++ plus Haskell plus Hart. And I just love these little dotted line relationships between languages, sort of knowing what are the primary influences that that influenced a language and why it was created. So that brings us to the end of that digression. And so this whole introduction section is wrapped up with the following slide that's saying every single programming language, or I shouldn't say every single programming language, but many programming languages have a language facility that is similar to what we're going to be covering in today's talk. So the 5 that we're going to be covering are C++ concepts, Rust traits. All right, we are done with this T. Rust traits, Swift protocols, Haskell type classes, and D-type constraints. But we're only going to be focusing on those 5. But know that there are other language facilities, such as TypeScript, structural interfaces, Go interfaces, modules, signatures, etc., that could be covered in like a full day class, but we've only got 90 minutes today or 75 minutes. So we're only going to be focusing on these 5. With this brings us to the end of the introduction section. So I'm going to click on the Q&A. I currently don't see any questions, so I'm going to continue to move on. And if you do have questions, feel free to put them in the chat, and we will pause at the end of the generic and parametric polymorphism section as well, to see if there are questions at that point. So section number 2, generics and parametric polymorphism. So we're going to revisit the 1988 paper by Philip Wadler called How to Make Ad Hoc Polymorphism Less Ad Hoc. And the things that I want to highlight from this talk are 2 definitions, one of ad hoc polymorphism and one of parametric polymorphism. So first up is ad hoc polymorphism, which the paper states ad hoc polymorphism occurs when a function is defined over several different types acting in a different way for each type. The paper then goes on to define parametric polymorphism, which occurs when a function is defined over a range of types acting in the same way for each type. So the 2 examples that they give are for ad hoc polymorphism, you can have multiplication for integer types, which is 3 times 3, or floating point types, which is 3.14 times 3.14, and you get different behavior. And then the example they give for parametric polymorphism is the length function. So you can have an array or a string and a generic function length that is going to have the same behavior across different types. So the way that you can kind of summarize this is the following. You have ad hoc polymorphism versus parametric polymorphism, both of them for function names when they have the same function name and the same or different types. Parametric polymorphism has the same behavior, whereas ad hoc polymorphism has different behavior. So superficially in C++, we have support for parametric polymorphism through our templates, and we have support for ad hoc polymorphism through function overloading in C++. And I really, really love parametric polymorphism. And I didn't realize this until I learned Go. So Go is an extremely interesting language, and we're going to take a minute, or a second to look at a quote or a video clip from Kevlin Henney, our keynote speaker from yesterday, on what his thoughts on Go are.
Now, here's an interesting one. So this is Go, which has been described as a very opinionated language in terms of its style and its design decisions, many of which I find incredibly easy to disagree with.
So I think it's super funny that Kevlin's saying that I completely agree. Go is a very, very opinionated language. They draw a circle and they want you to stand in that circle. And so that's just, it's useful to know because we're going to hop back to this example. And this example does not compile. And so I'm going to pause. Does anybody know in the chat why this example does not compile? It is not, well, it could be. Bronek has said int. Unused, println requires a string. Nope, none of those. Bronek might be correct when he's saying quote int, end quote, depending on what they mean by that. But the reason is that math.min only works for float 64s. So if that's what Bronek was trying to say with the int, then they were correct. So if you try and run this, you're going to get cannot use type int as a type float 64 in argument to math.min. So the A and B here are expected to be float 64s. So in order to get this to work, you have to cast A and B first to float 64s, then you get back a float 64, and then if you want C to be an int, you have to cast that float 64 that you got back to an int. And this is because Go famously does not have support for parametric polymorphism. When we write a max function or a min function in C++, we can make it work on any number of types. But in Go, you would have to explicitly write like min and then min int, or do something a little bit fancier because they don't have support for parametric polymorphism. And this was highlighted in a talk by Philip Wadler, the same individual that wrote the 1988 paper that we just looked at. So let's take a look at this audio clip.
There's this programming language called Go. I knew absolutely nothing about it, except that it's very widely used by some people. And I knew that it didn't have parametric polymorphism as part of the language. And I get a letter from Rob Pike, who I know. We used to work together at Bell Labs. And he wrote to me, said, would you be interested in helping us get polymorphism right and or figuring out what right means for some future versions of Go?
So this is super fascinating because the last time that I gave this talk, this was sort of the end of this story. So Philip Wadler gave this talk, I believe it was in June of 2020. And since then, now that we are in March of 2021, this, I guess, collaboration has turned into an actual proposal for generics for Go. So you can see this was released on January 12th of 2021, literally 2 months ago to the day from when I am presenting this talk currently. I guess it'll be a bit later if you're watching this on YouTube. And I believe this proposal came out of this collaboration. So I'm not sure if Go, for a long time, it's been said that Go 2.0 was going to have generics. So I'm not sure if Go is actually going to be coming out with a 2.0 version or what's going to happen with this proposal. But the whole point of this digression is that I realized my love for parametric polymorphism when I went and learned Go and then realized that it had no support for parametric polymorphism, and it requires you to end up duplicating a lot of the code that you're writing, which I find highly irritating. So I think this will be awesome for Go developers if this ends up getting into the language. And the last thing that I want to highlight in this section on generics and parametric polymorphism is a super random paper that talks about lightweight parametric polymorphism for Oberon. And it's because when I was reading through this and preparing for this talk, there was a really great quote that basically informs my mental model for type constraints versus types and types versus values. So the quote says, we introduce parametric polymorphism via our previous example. A type may be parameterized on types in much the same way a procedure may be parameterized on values. So the way that I think about this is the following. Type constraints are to types as types are to values. So when you have a type, like an integer, it defines the values that that type can assume. And the same thing can be said for type constraints. A type constraint provides basically the set of types that the type constraint can assume. And I've been told that this is technically incorrect. but it's a mental model. And I've also heard that all models are wrong, but some are useful. And I find this mental model very useful. So yes, this brings us to the end of section number 2, at which point I will pause again and check the Q&A to see if there are any questions at this point. I once again do not see any questions. So we will continue to move along, but feel free to ask any questions. Actually, no, one just came in from Peter Summerlad. Would one name a type system for types a meta type system? I guess you could. I mean, you can name it whatever you want. I sort of like the name type constraints, but a meta type system sort of fits. And as you'll see, and as we saw earlier, every language sort of calls this something different. They put a different label on it. And so, but yeah, if you want to think of it that way as sort of a type constraints or type system, a meta type system, definitely. So, answered that one. A question just came in. Are there a list of references at the end? Yes, I will provide links, but it's the same link that you saw at the beginning underneath my talks repository. All of the links are in a file called links.md, which I will show at the end of the talk. All right, that's all of the questions at this point. But like I said, feel free to ask questions, and we will take a break at the end of the 3rd section and 4th section to answer those questions as well. So let's move on to the more interesting part of this talk, which is the examples. So the first example is a super simple example, but I find it extremely illustrative to show some of the differences between these language facilities. And that example is adding two integers. So very straightforward. I assume all of you know how to do this in whichever language you consider your primary language day to day. In C++, that's my primary language day to day. It looks as follows. So hopefully this is super familiar to all of the C++ developers, either watching live or watching in the future on the internet. And the only thing that might be a little bit surprising if you haven't been keeping up with the sort of C++ 11, 14, 17 is the trailing return type, which is my preferred way to write functions because it's more similar to other more modern programming languages and functional languages. But this, someone mentioned in the chat const expr. Yes, we could put const expr if we wanted, but this is, we're trying to highlight just going from a simple adding function to a generic adding function. And so this is what it looks like in C++, 2 integers, a and b, and then we're just returning a plus b. So let's put this at the top of our screen. And we're now going to look at what this function looks like in D, Rust, Swift, and Haskell. So D is up first. It looks honestly identical, and we could have written this the exact same way in C++. The only difference here is that there's no trailing return type in D, so we can't use the trailing return type that we used in the C++ solution. Otherwise, these two are identical. For Rust, we have the following. So note, Rust mandates trailing return type. They don't call it trailing return type because that's just how functions look like in C++. And instead of int, they have i32, and they name their parameters before they list the type. So it's a:(i32). And also, very interestingly, there is no return and there is no semicolon. So in Rust, the last expression in a function, if that is your return value, you can omit the semicolon and the return, which I think is quite nice, especially for these super simple one-line functions. And yeah, I saw a couple other folks mention no discard and no accept for the C++ solution. Yes, we could definitely add those, and that is the best practice thing to do. Swift, we have the following. So instead of the 2-letter fun, we have the 4-letter func. And instead of int or i32, we have a capital I int. And note, we have trailing return type as well. And similar to Rust, we do not need a return or a semicolon for the last expression in our function body. And then someone also just mentioned that, yes, you can make the parameters const, at which point we're going to need a bigger slide. But yes, the C++ add is just a very simple version of the add function, not the best practice version. And last but not least, we have Haskell, which doesn't look anything like the other solutions, and that's because it's an entirely different language. It's a purely functional programming language. The way you can think about this is that the first line is the function declaration. They call them type signatures in Haskell. And everything but the last type is basically an input argument. That's not actually what's happening here, but coming from sort of imperative languages like C++ and Rust, that's the way you can think of this, is that the first two ints are your input arguments and the last type is your output argument. And then here, you're just declaring your definition of your function as a plus b. And yeah, someone actually has pointed out a version of add that we're going to see in just a second. Auto for all the languages, I don't think, yeah, most of these languages don't have support for auto, but many of them do have very good support for type inference, which is an adjacent language facility. So if we take all 5 of these function definitions, we can put them at the top. Then we can reformat them so that we line up sort of the function bodies and the return types as best as possible. And then we can do a summary of the comparisons between these languages. So this is all just sort of syntax and doesn't mean much, but as a programming language enthusiast and a potential programming language designer, I find, looking at this stuff side by side interesting. So the keyword before the function in all of the languages are as follows. C++ is auto. D is just the type of your output. Rust is fun, the 2 letters FN, and then Swift is func. Haskell doesn't have anything. Note that I tweeted something out a couple months ago saying, what is the keyword of every language before a function? And then many people took me to task over auto, saying that auto does not declare a function. That is true. You can use auto in many, many different cases, but it is the keyword if you want to have trailing return type that is going to become before your function declaration. So note, auto can be used many places, not just before a function declaration. For our integers, C++ has int or int32_t, and then D has int as well. Rust has i32, and then Swift and Haskell have int with a capital I. Trailing return type, the only language that doesn't support trailing return type is D, and then is the return necessary? Only in C++ and D. I can see we have a question, so we can actually answer it now. Which language would allow type deduction, aka auto add paren int a, int b, return ab? I don't actually know off the top of my head. I know Haskell and C++ do. I don't think D does. And I'm pretty sure Rust, you have to be explicit about your return type. And Swift, I'm not sure. But folks in the chat can correct me if I'm wrong, or if you're watching this on YouTube, please feel free to add a comment if what I just said was incorrect. Moving on to a digression, which is on the keyword that shows up before functions. So like I said, I tweeted this out a couple months ago, and here was the tweet. It is a very large graphic of sort of what functions use to indicate that we have a function declaration. So if we zoom in on this, the most popular is def. And that's because languages like Python and Ruby use it. And I think that influenced a bunch of other languages that were created later, such as Elixir, Scala. And of these languages, I think Crystal is the most interesting. Crystal is basically statically typed Ruby aimed at having the performance of C. So if you're familiar with Ruby, but you want more performance, Crystal is a language worth checking out. And then Fortran at the bottom uses function, which is the second most common. I believe Fortran also has a keyword subroutine. If we scroll down, you can see JavaScript, Julia, and Lua also all use function. And then the third most common is func. Nim is extremely interesting because func, I believe, is actually just a shortcut for no side effect proc. So there are 2 keywords in Nim for declaring a function, proc, P-R-O-C, and func. And func is basically just a no side effecting proc, which not many languages have language support for defining functions that don't have side effects. So I think that's super cool. And last but not least are Rust, Zig that have fun, Clojure, which has defun, which I think technically is a macro, and then Kotlin with fun, and then just the one-offs. And I think I like fun the best from Kotlin because it spells out fun, and programming is fun. Which is probably what I would choose. Yeah, someone in the chat just said Crystal hasn't hit 1.0 yet. Yeah, I think it's a very, very young language that's still in development. And yeah, someone said +1 for Nim. All right, end of digression. Back to our examples of adding 2 integers. So these are the non-generic implementations of adding two integers across these 5 languages. Now what we're going to do is we're going to take these 5 implementations and turn them in from non-generic functions into generic functions. So first we're going to do it for C++. And if you're a C++ developer, you probably know the way to do this is with a template. So we can replace our ints with a template type name T, and then everywhere we saw an int, we can just replace that with a T, and we're done. Some of you might be thinking, and I know someone in the chat earlier said this, that in C++ 20, we can actually write this slightly differently in a way that I actually prefer. I'm not sure if this is going to be considered non-best practice in the future, but you can actually just use auto now. And auto is basically the exact same thing. It's just a different way of spelling what we just spelled using the template type name T. There are slight differences in that, like you can't constrain. We constrained previously that both A and B were of the same type T. Here, I believe that's not the case. But still, nice to note that you can use 3 autos in our function declaration now for our C++ function. Yeah, someone, Mike in the chat just mentioned it's not because A and B can be different types. So it is slightly different. And then Peter says, please do not define an addable concept. We won't be doing that in this talk, so I can't speak for the rest of the C++ community, but not in this talk. Moving on to D. D looks very similar to C++, but instead of using angle brackets, it uses an extra set of parentheses plus the template name or in front of our 2 parentheses. So we have now T add, paren T paren, and then we replace each of the ints that we had before with a T. So very similar to C++, just instead of angle brackets and having to spell out template type name, they use parentheses. In Rust, it looks as follows. So very similar to D, except instead of parentheses, we're now using angle brackets. And once again, we're replacing each of the I32s with the template type T. So now it's angle bracket T, angle bracket, and then A:(T, comma B:(T). Everything else stays the same. For Swift, it is very, very similar to what we saw in Rust, almost identical. We're replacing our ints with T and then putting an angle bracket T in front of our argument list. And last but not least is Haskell. And Haskell replaces each of our ints just with a T, or any letter for that matter. It doesn't have to be a T, but just to be consistent with the other generic implementations across Rust, D, C++, and Swift, we're calling it T, but I think more idiomatically, you would call this A for any type in Haskell. All right, I'm going to pause now and ask the audience, which of these compile? Because we have 5 different generic implementations of the add function on our screen, but not all of them compile. So can anybody tell me which of these solutions do compile? So Peter said C++, which definitely compiles. And then Dima says it depends on how you use it. Demetrio says Rust does not, so that is correct. Rust doesn't compile, C++ compiles, and a couple of people saying it depends. So yeah, I guess maybe depending on the context that I compiled this in. But generally, the point that I'm trying to get at is that only C++ and D compile. And that's because we need to add something to the Rust, Swift, and Haskell solutions in order to get these to compile. And those are the following. So for Rust, we need to add this trait, std : ops : add, and then output equal to T. For Swift, we have to also add a protocol, which is the numeric protocol. And for Haskell, we have to add a type class on T, which is the num type class, which you do with this num T and then a fat arrow with the same T, angle T, angle T. And this is probably the most important thing that I want folks to take away from this talk, is that I consider there to be 2 categories of this sort of parametric polymorphism language feature, whether you're calling it concepts, type constraints, traits, protocols, or type classes. These fit into 2 broad categories, which I am calling the following: type constraints versus type classes. So note that, each of these correspond, type constraints corresponds to D and type classes corresponds to Haskell, but I'm using these as broad categories for the categories that each of these language facilities fits into. And the main thing that differentiates these two categories is that type constraints constrain and type classes consent, meaning that with C++ and D, you start with the world, and then when you add either a concept or a type constraint, you are limiting what can be passed into your generic function. Whereas with type classes, you are consenting. When you declare a generic function and you don't say anything about that function, you can do 0 things with that. And you need to add type classes or traits or protocols to that generic function in order to let the compiler know this function with the types that are provided is able to do the following, is able to add, is able to compare, etc. And for me, the best way to sort of look at an example of this is by looking at the simplest version of a generic function, which is the following. We're going to look at C++ and Haskell, and we're looking at a function that takes a generic type T and returns a generic type T. And the difference between the C++ solution, which is just template type name T, auto F, T, T, arrow T, and then Haskell's, which is just F, : T, arrow T, C++'s function theoretically can do anything because our generic is completely unconstrained. Whereas in Haskell, you can do exactly one thing because we haven't told the compiler what T can do. And the one thing that we can do is just return back the T that we gave the function F, which seems very useless, but this is actually a built-in function to the Haskell prelude, which I'm sure a few of you know, which is the function ID or id, which is short for identity. So it's the identity function. It's a function that just returns the argument that was passed in. And curiously enough, in C++20, we actually added this to our functional header. So we now have a function object in C++ that is doing the exact same thing that we see on the screen here for Haskell and C++. And you might think, like the first time I think I heard of the identity function was on a podcast called LambdaCast. I thought that sounds incredibly useless. What would you ever want a function for that just returns you back what you gave it? But when you start doing a lot of functional programming things where you're working with higher order functions that expect functions as arguments, especially multiple functions as arguments, sometimes you'll want custom behavior for one of the functions that you're taking as an argument, but for the other one, you just want to do a no-op. You just want to return back what you are being given, which is exactly what identity is for. And so yeah, I'm going to hop back now to one of the clips that we saw earlier from the LLVM 2017 talk called Implementing Swift Generics that was given by Slava Pestov and John McCall. And it's interesting that they call their generics constrained generics, even though that's sort of the opposite of what I just explained. They basically go on to say that the unconstrained generics are the ones that can't do anything. Which seems completely counterintuitive to me, because if you have something that's unconstrained, like semantically to me, that seems like you're saying that you can do whatever you want. There's no constraints. There's no constraints. Do whatever you want. But here they're saying when you have an unconstrained generic, that's when your behavior is limited, or what you can do with your function is limited. And the second thing I want to highlight from this talk is that earlier when Slava Pestov was presenting, they had a slide which highlights what they call their parametric polymorphism, aka protocols, bounded parametric polymorphism. And this is something that I'm going to talk a lot more about in the follow-up 2.0 version of this talk. So in the literature, they refer to this type of parametric polymorphism as different things in like every single paper. I've heard it referred to as bounded parametric polymorphism. I've heard it referred to as constrained parametric polymorphism. In one of the papers, it seemed like they were inventing sort of new words, and they were referring to the two different categories as nominal and structural. I can't be 100% sure because a lot of these papers were 50 to 80 pages long, and I did not read them through fully. But expect in part 2 of this talk for me to go through the full literature and really break down, what are the different categories, what are the names in both sort of industry and programming languages in the academic literature, because this is sort of a point that I find very confusing, is that there doesn't seem to be agreed upon terminology when it comes to this sort of category of parametric polymorphism where you are bounding or constraining your types. So once again, just to recap, we are going back to our two different categories: type constraints, where you're constraining what you can do with your function versus type classes where you are consenting. You are starting off by only being able to do the least amount, and then by adding traits, protocols, or type classes, you are enabling your function to do more. And with this brings us to the end of our first example. So I can see that I have at least one question in the Q&A. Bronek asks, would you consider these both parametric as opposed to ad hoc? I am going to assume that the both is referring to the two different categories, although I could be incorrect there. Oh, so yeah, Bronek followed up with a yes. Yes, I would definitely consider these as different facilities either providing support for or superficial support for parametric polymorphism. So it's important to note, or maybe not important to note, but technically speaking, C++ templates are not supporting parametric polymorphism. They are not a parametric polymorphism language facility. They superficially give support for it, because what templates are doing behind the scene is they were going and they're stamping out all of the different versions of that sort of template function that you need for each of the times that it's called. So at the end of the day, you don't have a single function. You have a bunch of individual functions that have been customized for the types that you're calling that function with. So it's technically not parametric polymorphism by the textbook definition, but it is superficially giving you support for that language facility. So answer live done, answer live done. An anonymous attendee asks, is there room in C++ for type classes? Well, so arguably concepts is our support for type classes. And I would encourage you to take a look at a paper that just came out in the most recent C++ mailing by Barry Revzin. I believe it's called, just search for, I can't remember if it's tag invoke in the title or customization points, but basically Barry Revzin in the most recent language evolution working group meeting gave a fantastic presentation comparing the different solutions for things that we are trying to solve with concepts and how basically we've really fallen short. And at one point in the presentation, he compared our current C++ concepts to Rust traits and showed how much more flexible the Rust traits are. So I can also find a paper if you find me after the talk. I can link that paper to you once the talk is over. But I think we're going to get closer to what is possible in other languages, but I don't think ever we will have exactly type classes because Haskell is just such a different language. Meg is asking, does template specialization introduce ad hoc polymorphism? Does template specialization introduce ad hoc polymorphism? Technically, yes. I would say yes to that answer. So when I think of ad hoc polymorphism in C++, the first thing I think of is function overloading, but definitely specialization gives you the exact same thing, a different behavior based on types. So yes, that's definitely a correct way to think about things. And yeah, Lucian is saying yes as well in the chat. All right, that is the end of the question queue. So once again, if you have questions, feel free to ask them, and we will revisit them both at the end of the talk and at the end of the next section. So our final example is a bit more involved than the example that we just looked at, and it is going to be the following. We are going to create two different shapes, a circle and a rectangle, and then we are going to define some functions on the shape, primarily area, perimeter, and name. And then we're going to write a generic function that prints out the information of a object, either a circle or a rectangle, based on the different implementations of your sort of area and perimeter. Oh yeah, and Roger Orr has linked the paper, We Need a Language Mechanism for Customization Points. Thanks, Roger. That's awesome. Yeah, and it's a fantastic read. Barry's papers are marvelous. His ones on the pipeline operator is also fantastic. If you ever want like introductory sort of papers that are more digestible, I can't recommend Barry's papers enough. But yes, example number 2, shapes circle and rectangle. So let's take a look at our C++ example first. So we're just going to declare our 2 classes, circle and rectangle. So if you're a C++ developer, this should look quite familiar. Once again, as we have in the past with our C++ examples, we're using trailing return type. So for name, we have a function that's just returning a string. For area and perimeter, we're returning floats. And you can see the implementations pretty straightforward. For circle, it's just pi r squared. Perimeter is 2 pi r. And then for rectangle, we have the equivalent formulas: width times height and 2 times width times 2 times height for our area and perimeter. Note that it's not best practice to call your member variables single character names like R for radius and W and H for width and height. Use better names, but because this is slideware and already there's quite a bit of code on the slide, I abbreviated the member variable names to be single characters just for brevity. And yeah, I don't think there's much else to say here, other than the fact that it's a bit irritating that we got the defaults wrong in C++ however many decades ago, and that we have to add the const here in order to make this a non-modifying function. It'd be nice that by default it was non-modifying, and if we wanted to have a mutating function, we did something similar to Rust. But c'est la vie, that ship has sailed. But otherwise, I think it's quite nice for C++. Moving on, and explicit as well. Yes, Ricardo has mentioned that that's also a default that we got wrong. But what can you do? Moving on to our D solution. So this looks very similar. The constructor is slightly different. You have to use the this keyword. But other than that, we're also using Pascal case because that's more idiomatic in the D language. Other than that, though, it looks quite similar. Once again, we have the const keyword to let the reader and the compiler know that this is a non-modifying function. Oh yeah, and I forgot to mention that maybe the coolest part of the C++ solution is that we're actually making use of C++ 20's math constants with pi, which also D has through their constants. So yeah, I think it was a mistake that D didn't seize the opportunity to correct the default of having to add the const to your function declarations. But Rust and Swift got it right. So, you know, you win some, you lose some. Other than this, though, these two look very similar, the C++ and the D solution. Moving on to the Rust solution. So the Rust is quite interesting. This is starting to look slightly different. One of the key things here that's different is that you can't just return a string literal here. You have to use a conversion method called toString, which is interesting. I learned that while putting these together. And you'll also note that you don't see any consts anywhere. So by default, functions in Rust are non-modifying, and that you have to add a mute to the self parameter in order to have a modifying function. And I think this is definitely the correct default. Other differences, instead of float, we have F32, and that we define our struct sort of up front, and then we do these impl, which is sort of for implementation down below. Other than that, I think it looks pretty similar. You know, we should be getting used to seeing these. We should be getting used to seeing these sort of implementations for our functions: pi r squared and 2 pi r, w times h, which is width times height, and 2 times width plus 2 times height. Moving on to the Swift solution, this probably is my favorite solution, actually. And one of the things I'll say about Swift is I'm not a Swift developer, but when I was writing up these solutions for Swift, I basically just wrote the code and it always worked. Swift is an incredibly nice language to transition to, at least from a C++, coming from a C++ background. So many times I would just write the Swift code and then that would be the correct code. Whereas Rust, a lot of the times, I would get compiler errors. The compiler errors are absolutely magnificent. And we're going to have a digression about that in the future. But it's really, really nice. It's a really nice experience coming to Swift, writing the code, and then it just sort of works, which is super, super nice. Once again, a couple small differences that the constructor is using a init here for Swift. And we're once again using Pascal case because that's idiomatic in Swift. But other than that, it looks very similar to what we had in the other solutions. And last but not least is going to be the solution that is most different. A pattern that we are starting to see is Haskell. So here we are using record types at the top with the data keyword in order to define our record circle and record rectangle. And then we have a bunch of functions that are sort of free functions defining our name, area, and perimeter for both circle and rectangle. Note that this actually does not work because we don't have function overloading in Haskell. So here we have same named functions, name, area, and perimeter for both circle and rectangle. However, this is not going to compile. I'm setting this up because it'll have a nicer transition later on in the slide deck. But if we want to get this to compile, we actually have to make these functions have different names. And if you're familiar with Haskell, you'll know that this sort of syntax is pattern matching a lot of the time. So when we have this record type and then the parentheses plus our type and then underbar, here we're basically ignoring the information that's stored in the record type and just returning circle. And then for other ones where we're doing the area and the perimeter, we're getting out the radius and the width and the height and then doing something with that. So anytime you need to discard information, you can just use the underbar. And we might be getting something similar to that in C++ with pattern matching whenever that gets in to the standard. So this takes us through the setup of each of our circles and rectangles for C++, D, Rust, Swift, and Haskell. And so now what we're going to do is we're going to go back to our C++ solution, and we are going to add a print information function. And it's going to be called print shape info for each of our languages. And we are going to try and print out the shape, the name, the area, and the perimeter for each of our objects. And so for C++, this is what it looks like. We're using a snake case because that's idiomatic in C++. We're taking in a generic type at this point, which is unconstrained, S for shape. And then we're using format print. This technically, I don't believe is supported by any of the standard libraries currently, but it did get into C++20. And if you go to Godbolt, or if you look at any of the, like all of the code that shows up in this slide deck is also in the GitHub repository with Godbolt links. You can access Victor's format library on Godbolt, which is what the standard format was based on. And so I'm starting to use it just to get in the habit. And we get this a lot nicer than using std cout with the less than operator, which I think is super nice. And this works in C++ because we are in the type constraint model where we're starting with the world. We don't actually need to do anything extra here in order to get this code to work. Moving on to the D solution, looks somewhat similar. Here we're using right-lin. We don't have the sort of nice formatting capabilities of the C++ format print. So we have to do this sort of inline, but it still looks pretty nice. And once again, we have our generic function that takes a shape t, and that is sort of generic made by the paren t before the argument list. And once again, this works because we are in the type constraint model. So we don't have to do anything extra in order to get this to work. Mike says, I think that only std format made it into C++20, so you need to use the library in order to use format print. So that is true, but there is committee work being done to get a lot more of the format library that Victor's worked on into the standard. It's the same with C++20 ranges. C++20 ranges is based on Eric Niebler's range v3. And only, I believe it was like 13 range adapters got into C++20, and there's way more in range v3. And there's currently a proposal for C++23 to add a bunch more. So over time, we're going to see more and more of these libraries get into standard functionality. Moving on to the Rust solution. So this is what it looks like in Rust, very similar to what it looked like in C++. Instead of format : print, we have print line bang. But other than that, it actually looks almost identical, except that we have our angle T angle instead of our auto in our argument list to make this a generic function. But note, because we are now in the type class world, this no longer works. If we try to compile this, we get the following. Name, area, and perimeter are not found on the generic type T. And at this point, I want to highlight how amazing the Rust compiler is. If we take a look at the full message, whenever you have I shouldn't say whenever, but a lot of the times when you have a compiler error in Rust, the compiler gives you these help messages And they read, items from traits can only be used if the type parameter is bounded by the trait. The following trait defines an item name. Perhaps you need to restrict type parameter T with it. And then it suggests you that I should add :shape to my generic type T here. This is phenomenal, so much so that I want to go on a digression here on how amazing the Rust compiler is. And if you're a C++ developer and you haven't explored Rust, prepare to be a little bit sad because of how amazing the Rust compiler is. So for instance, these are just examples of things that over time, while I've been exploring the Rust language, how the compiler has basically like spoken to me, like talked to me, like, hey, here's what you might want to do. So when I was building up the circle example and I was defining the name function that just prints out a string, note that I said you had to add the .toString conversion method because you can't return a string literal. What did the compiler tell me? Expected a struct of std : string : found a ref string, help. Try using a conversion method, quote unquote circle to toString paren. So like, I didn't know what I was doing. And I made this mistake. And then the compiler immediately told me what I needed to do in order to get this to work. That is such a wonderful experience as someone who is learning and exploring a language. Another example, when I was building up the first exercise of creating a generic add function, when I did this, the compiler basically just told me what I needed. So like, even though I said Swift was a much nicer experience and then I just typed something and it worked, in Rust, I would type something, it wouldn't work, and the compiler would tell me what I needed to do in order to get it to work, which is just, it's such an amazing experience. I don't have to go to Stack Overflow. It just, it won't always tell you what you need to do, but a lot of the times it does. And I think this is the last example where this is something I really, really wish we had in C++. Here, I'm using the mute keyword to define a variable that is modifiable. So here is a circle C that I'm saying I'm going to mutate this in the future. However, if I don't go on to mutate it, the compiler will tell me, consider removing mute because you've declared this variable mutable, but you have not mutated it. So it could be immutable, which is super, super nice. I really wish in C++ that we had a static analyzer or a compiler warning that would let us know when we could make a variable const. I believe actually in Visual Studio, they do have a check for that, but currently for Clang, there's a proposed extension to Clang Tidy, I believe, that does the static analysis check, but it has not been merged the last time I checked. So yeah, this is just for any future people that are watching this on YouTube that are thinking about creating a language, please try and build this kind of stuff into your compiler. And I know C++'s compiler today is like an order or 2 orders of magnitude better than it was 2 decades ago. But I think we're far from like basically our compiler like telling us what we need to do. And this is some like super, super nice functionality. Peter's saying cvelop has a const checker that proposes quick fixes. Okay, that's super nice. So there are a couple, I think, tools out there that give you this ability, but I have not found any open source, like free ones through Clang Tidy yet. But I hope that in a decade we have those. So this is the end of the digression. I just want to highlight like how wonderful the Rust programming language is when it comes to sort of assisting you, because it does have a steep learning curve similar to C++, but I think their compiler does a much better job of like helping the new programmer. Jonathan in the chat says, in Elm, they refer to this idea as compiler-driven development. Yeah, I've heard the same thing of, I think No Red Inc., they use Elm quite a bit. Like they're the primary company, and they've been on podcasts talking about how, yeah, that's like a fundamental value for Elm is that if we're going to sort of be more constraining in what you can do, we're going to let the compiler really, really help you out. So like half the time, the compiler is just writing the code for you, which is super nice. And Ricardo linked to highly recommend reading this elmlang.org news, compiler errors for humans. So yeah, thanks for sharing that. That's super awesome. But yeah, this is the end of this digression. Let's get back to our generic print shape info functions. So for Swift, we're switching to camel case because that's idiomatic. And this looks super similar to the D solution that we saw earlier. We're printing each of the shapes and then inline doing this s.name, s.area, s.perimeter. Once again, this is not going to work in Swift because we are in the type class world. So for our type T here, it's going to say has no member name. And finally, for Haskell, we're going to skip this one. Technically, we could get something working, but really in Haskell, it either works or it doesn't work. You can't really build up a solution and then get like a nice message. So for Haskell, we're going to skip this, and we're going to come back to it when we actually are setting up our type class. So let's loop back to our C++ solution. So this works, but now we're going to define our concept. So very simply, this is all we need to do. Template type name S, where S is our type, our generic type T or S. And then we have concept shape, which is going to be the name of our concept. And then we go requires with our generic type S. And then we have two braces, and basically we put all our constraints inside these braces. So we're saying we want a function called name that returns us a string. We want and then two functions, area and perimeter, that return us floating points. And then once we have this concept, all we have to do is in front of our auto in our argument list is insert our shape concept, and we're good to go. And so now we've constrained our generic function print shape info, and we're good to go. Note that there are like 3 different ways to spell this. Technically, we could keep our template type name above our generic function and then replace the type name with the concept. And I think there's another way to spell this as well. This is my favorite, but we're very early in the C++ 20 sort of concept era, and I'm sure there will be best practice coming out on this in the future. So this is super cool. Like I said, it worked before, but now we've defined a simple concept that we can use on our generic functions that are supposed to work on shapes. And anytime we pass it something that doesn't conform to this concept, we're going to get a nice compiler error. Moving on to the D solution. Once again, this worked before, but now we're going to define a type constraint for D. This is a little bit noisy. It's definitely the least clean of the 5 solutions. So here we go template shape with our generic type T, const shape in order to name our type constraint. And then we have to, unfortunately, go underbar traits, paren compiles, comma, and then our generic type T. And then once again, inside the braces, we set up all the requirements. So here I left out the type constraints on the output type, but we're saying that we basically want a name, an area, and a perimeter. So although the type constraint is a little bit messy to define, using it is actually quite nice. And we use it with what I think is a super nice way of declaring this is basically just an if statement before your braces, before the declaration or the definition of your function, but after the signature of your function, which I think is really nice because even if you don't know anything about concepts or type constraints, if you read something like this, here's a function if, and then a concept, you can almost guess that this is doing something to sort of constrain when this function is usable. And that is that for our D type constraint. Now moving on to the type class world of Rust, Swift, and Haskell. And for Rust, we are going to have to do the following. So I have impl circle and impl rectangle omitting sort of the body of these because we're going to need to make changes to this. And now we're going to define a trait. So we define trait the same way that you might define like a class in C++. And then we're just basically defining the signatures that we want our trait to conform to. So this is super nice. Name, area, perimeter that return us a string and 2 float 32s. And then note that if you saw the animation, we're going for an impl circle and impl rectangle to impl shape for circle and impl shape for rectangle. And so similar to C++, all you have to do is set this up. And then once we've done that, we need to add to our generic type T a colon shape. And now we have constrained our Rust function. And this will work at this point. We will no longer get a compiler error. So I think that's all I want to say about the Rust solution. Moving on to the Swift solution for the protocol. Once again, I'm showing the class rectangle and class circle omitting the bodies because we're going to need to make changes to these 2 classes in order to use the protocol that we're about to define. So we need to set up a protocol very similar to how we set up the trait in Rust and the concept in C++. This is probably the cleanest and the nicest in my opinion because it just looks so clean. We have protocol the same way we use trait in Rust, and then we're defining the signatures of the functions that we want. So we've got a function name that returns a string and then area and perimeter that return 2 floats. And then once again, the same way that we had to add to our class rectangle and class circle for the impl in Rust, we have to now do something that looks like inheritance, but is not really. We are just saying that we have a class that conforms to this protocol shape. And once we've done this, That's all we need to do to set up this protocol in Swift. We just want to add the colon shape to our generic type T in the angle brackets, and we're good to go. And last but not least, we have Haskell. So I've gone back to the original version where we called these both name and area because it's going to lead to a more beautiful code transition. But now what we're going to do is we're going to set up a type class and define the following. So we're going to move things around here. So here we have our type class shape A, where A is a generic type. And then it has the following: a name that goes from a generic type A to a string, and then two functions, area and perimeter, that go from a generic type A to a float. And once again, we have our record types, circle and rectangle. And now we just have our shape type class that's being implemented for each of our circle and rectangle shape. So for circle, we're basically just taking the definitions that were free functions before and slotting them into this instance shape circle where, and then we're doing the exact same thing for instance shape rectangle. Note that this looks like a lot more code than we saw previously, but that's because we're including more than we needed to. We're including these definitions inside the instance shape circles that we were not including in the previous examples. So if we omit these, this is actually closer to what we were showing for the previous examples. And I think this is actually quite nice. And note that there are a couple different ways to do this. You could define like a sum type that is a shape type that consists of either a circle or a rectangle, and then do the type class implementation all at once using pattern matching, which I think is more idiomatic. But just in order to compare these to the 4 previous examples in C++, D, Rust, and Swift, I was trying to keep it sort of as similar as possible. And then of course, at the bottom here, we have our print shape info, which we're seeing for the first time, which is basically doing catenation of strings with the ++ operator. So yeah, this is basically the end of our second example. So at this point, I'm going to pause before I get to my final thoughts. And let's take a look at the question. So Peter is... I think he's actually just making a statement that C++ OX had concept maps, which of the languages allows something similar to map differently named functions to be considered as one of the concepts. So yeah, there was a paper that got highlighted in the clip from Context Free that also Dave Abrahams was referring to, that I believe you can find in the resources linked in the GitHub repo, where all the code and the slide decks and the links are, that basically goes over what we lost out. We went from like concepts OX to concepts light, and we lost a lot of stuff in that sort of transition to concepts light. But yeah, it's a great point. Thanks for pointing that out, Peter. And then Tristan asked, will I be talking about C++ OX concepts at all? No, I did not go into that rabbit hole. I will in the 2.0 version of this talk. And there's actually, I found a great clip at the end of a C++ Now talk from, I believe it was 2015, where there was a presentation on Concepts Light, and there was like 10 to 15 minutes of discussion at the end of that presentation on sort of the differences and the pros and cons between the two different. And then Tristan followed up saying, Doug Greger worked on them before Swift. They offered both consent and constraint options, as I understand it. But that complexity was probably their downfall. So yeah, look forward to the 2.0 version of this talk. And then Peter asks, how can you map existing types that almost fit, but that you cannot change to fit? I do not know. Let's chat about that in the hallway afterwards. Yeah, let's talk about that afterwards. Or if you have an answer, someone in the chat, feel free to answer in the chat. So once again, we're going to leave. It looks like we've got 10 minutes left. So the last section should take about 5 minutes, where we'll have 5 minutes at the end for questions. So yeah, this is just my final thoughts on the different 5 languages in going through the exercise of writing up these 2 different examples. And some of these are like fluffy comparisons. So, take it with a grain of salt. It's all completely biased from my point of view. But yeah. I think it's useful to look at these different sort of metrics. So final thoughts. The first one we're going to look at is time to implement. So I kept track of how long each of these took me to implement. This one's focusing primarily on the second example. Swift was the fastest, D was the second fastest, then Rust, then Haskell, and then C++. That might be a bit surprising, seeing as I'm a C++ developer. But I think part of the issue is that when I was developing these, the compiler support for these is sort of, it was coming out. We're still getting support for C++ concepts across different compilers, whereas every other language has these language facilities, the tutorials, the resources, the documentation, all built out entirely. And like I said, going from Swift to Swift from C++, it just seemed like every time I coded something, it ended up working. And then, yeah, Rust and Haskell, I would definitely put on sort of the steeper learning curve languages. So not surprising to see them at 3 and 4. The second metric is lines of code. So Haskell, not surprisingly, is at number 1 with 25 lines of code. Then Swift, then Rust, then D, which are all quite close. And then C++ is a close 5th. Note that the initial time I presented this, I actually had C++ at more lines of code than it needed to be, and it dropped down about 12 or 13 lines to 47. And also, like, take this with a grain of salt, because different languages have like imports that are necessary, whereas other languages don't. So this is all, you know, you could put like a plus or minus 5 probably on each of these, in which case this is just a no-op, except Haskell probably will always win in first place. But then the other 4, depending on, you know, how you format your code, and whether you count like the white spaces and the imports, you know, this is going to move around entirely. And my favorite metric of all is the pleasantness, which is what this happy face represents. So I found Swift by far to be the nicest, just due to the fact that every single time I wrote something, it seemed to work. Rust was a close second in that even though I would write something and it wouldn't work, the compiler would immediately tell me how to get something to work, which is fantastic. D was okay. I think that D unnecessarily added more complexity than they needed to the language. You know, for instance, C++ has like the const keyword, and D has like, you know, 3 or 4 more keywords. They have const, they have immutable, they have, I think, pure. And I think that there's an unnecessary level of complexity that was added. Haskell is super nice, but definitely it's a steep learning curve, and C++ is C++. So I think I have some bullet points that I just want to highlight. Half the time I just guessed right for Swift. Chris Latner, the designer of the language, has this value that was embedded deeply into the language called PDOC, progressive disclosure of complexity, which is also known as being infinitely hackable. This is the idea that like you want the language to start out feeling like Python, but then if you want, you can like lift the hood of the language and then get more down into like the C++ side of things if you want to. And I think they did an amazing job at this. And defaults are all correct in Swift, which is nice. Rust, as mentioned before, compiler messages are amazing. Defaults are all correct. D seems a bit too similar to C++ when you add that there's a lot of complexity in certain places. Haskell's got a steep learning curve, and the compiler messages are bad, which is something that I'm very thankful that Rust did not adopt. And C++ has 40 years of history, which means there's going to be less elegance when you design language features, you know, 40 years later, which is it's just the way it is. Most of the defaults are wrong, which is just unfortunate. You know, there's nothing we can do about that now, unless if we decide to break ABI in like a massive way, which is never going to happen, probably. And then C++ 20 is still a work in progress, as I mentioned before. So last but not least, I just want to highlight some sort of programming language ranking sites. So this is a site called Languish that was built by the same individual, Context Free, that we saw a clip for earlier in the talk. It measures different statistics on GitHub, and this is like an average of them. So C++, unsurprisingly, is at the top. Swift is in second. Rust is in third. Haskell in fourth. And then D is in fifth. If you take a look across different programming language rankings, TIOB, PyPL, RedMonk, and Google Trends, you basically get the same pattern every single time, except for TIOB, which ranks Haskell below D in this case. And I was super surprised at how high Swift ranked on some of these. If you take a look at the number of Reddit subscribers on the subreddits, this is the way it looks, at least as of a couple months ago. C++ is in first place, but Rust and Swift, considering that they've been around like for a fraction of the amount of time that C++ has been around, have got quite a few. And I wouldn't actually be surprised if Swift has more developers than Rust does. And that's because I don't think Swift developers primarily go to Reddit. I think they go to the Swift forums. So I think I don't have a Mac. I don't develop, like I don't have an iPhone. I don't have a Mac. I'm not an Apple developer. So I'm sort of removed from that community. But I think the Swift community is actually a lot larger than I would have expected. So once again, these are the final thoughts overall. I think it's awesome that all 5 of these languages have some sort of facility for a type class or type constraint facility. And yeah, all of the code, as I mentioned before, can be found at my GitHub repository talks under the 2021-03 ACCU folder, as well as the code examples and all the links. So there's a file called links.md for all the podcast links, the YouTube video links, and the papers and articles that I referenced. If I'm missing one that I referenced, which I don't think I am, but if I am, feel free to open a PR and I'll be happy to add it. And yeah, thank you. And I'm happy to answer any remaining questions that people might have.